Thanks for coming. Today we'll talk to you about how to start doing functional programming in Scala. I'm sorry, the title is a bit misleading. If you're a complete Scala beginner, maybe the code examples will be hard to follow, but I'll try my best. Who has written any Scala yet? OK, so I'll take some time to explain the examples. Just before starting, I'm pretty active on Twitter. So if you have questions or remarks or stuff like that, just tweet me, and I will answer on Twitter, which is nice for people who can't attend stuff like that. And also, I have a blog and stuff like that, if that's your thing. Just quick, before starting, take two. I'm working for a company called Cloud. That's a platform as a service. Basically, developers Git push their code, and we handle all the production stuff, like restart and failure, scalability, software updates, security updates, everything. It's our job, and our clients just have to push their codes, and that's the end of their responsibility. So if you want to try it out, just come to me afterwards. I'm the CTO of Cloud, but deep down, not just a CTO, I'm first and foremost a functional programmer. I started doing functional programming professionally in Scala, but I do it a lot in JS as well, either client-side or either server-side. Node.js is not that bad. We've all been to the keynote, and there were some hard things said about Node.js. Some of them are true, I won't lie, but give it a try. Like for simple projects with strong deadlines and no maintainability guarantees needed, then no, I'm serious. I have projects where I won't have to maintain the code, and Node.js is perfect for that. It's a bit more work to have maintainable JS, but it's totally doable. OK, so I will start with a very simple functional pattern. Normally, you've already seen it, but just to make sure you're following. It's a zygoastomorphic prepomorphism. Is that OK for everyone? Yeah? Does anybody need a generalized zygomorphism? No? OK. More seriously, I won't talk about functional abstractions today, or at least I think everybody has heard about functors and monads. I won't explain them. They are very well documented. I will explain how to encode that into Scala, because the documentation about the abstractions themselves are very abundant, and you won't have any trouble finding it online. But how it's encoded in Scala, it's not that well documented. And when you start functional programming in Scala, you're somehow expected to know Haskell basics and be comfortable with that, which is not the case of everyone. So that's why I made this talk. So today we'll just see very basic blocks of functional stuff. And if you want to read more about more high-level abstractions like functor, monads, catamorphism, stuff like that, then you will have the tools to do that. Since the constructs we're about to use are not directly encoded in Scala, like it's not expressed at the language level, we use encoding to do that. And there are many ways to do what I'm about to show. So keep in mind that I will try to show every time the simplest solution. It's not always the best, but it's the simplest and it fits on slides. And it's OK for most projects, but keep in mind that there are other ways to encode what we're about to see. OK. First thing first, Scala it's made for people who want both object and functional programming. The object-oriented part of Scala is very well documented because it's encoded at the language level. So every book about Scala will talk in excruciating detail about traits, trait linearization, subtyping, and stuff like that. FP, on the other hand, the FP community in Scala is like more or less all the thought leaders, whatever that means, are coming from a language like Haskell and stuff like that. And they sometimes expect you to know Haskell or ML or stuff like that. And then the Java, we just do that, the same thing, but in Scala. So that's good, but if you don't have training in ML or Scala, then, or Haskell, then that can be complicated. So we will encode stuff used in functional programming, but we will use Scala's object-oriented nature for the implementation. But it's much more about being an implementation detail than just pure design. So one important question remains. What is FP? It's a question with many, many answers. And one answer I like particularly, which is quite high level, is that functional programming is programming with values. Everything is a value, and you just have, your execution flow is just a data flow of data going from one function to another. It's not about closures or tail call elimination or very technical stuff. It just, everything is a value, and then you have your value flowing from one function to another. Which means expressions are very important when you practice a functional style. And that's a good thing that in Scala, almost everything is an exception. Like if block, it's not just a control flow block. It's an expression. It will resolve to either the first branch or the else branch. So you can, instead of having if stuff, then assign this value to this variable, then the if itself is an expression, and you got to think about it like that. An if block is there to produce a value, and then you get the value at the end of the if block. So it's a bit different. You're thinking about just a tree, then you're taking a branch or you're taking the other one, but everything is there to produce a value at some point. It's like ternary expressions in Java, for instance. I really like ternary expressions, not because they have cryptic syntax, but because ternary expressions in Java or in JS, they allow me to have if blocks as expressions, and that's very good. Ternary syntax, for those who don't know, it's like condition, interrogation mark, if true, colon, if false. So it's very hard to read at first, but the fact that it's an expression is very nice. Same thing with pattern matching. You don't see it as a switch, where in a switch you're saying the computer do this or else do that or that stuff. In functional programming, you're just deconstructing the value and producing a new value, making choices at some points. And this kind of thinking goes very well with a static type system, because since your control flow is now a part of your values, then your values have types, then you're able to use your type system to type check your control flow, which is very, very nice if you think about it. Like all the security issues in the TLS libraries, well, somebody typed go to fail twice. It wasn't detected because the type system is not able to detect that. If you're just using control flow as whatever happens, then you can't have the type system check that. If your control flow are expressions that have type, then you're able to type check that. And that's why functional programming and static type system go so well together. because programming with values allows you to use type system to check actually interesting values and actually interesting things. So you can detect logic errors in Scala because your logic is reflected into your control flow, and it's reflected into types, which is nice. And with that in mind, I want to talk to you about algebraic design, which is a fancy word for domain-driven design with functional tools. So algebraic design is like shorter and much more mathy, so it's better. But basically, the idea is the same. You like observe your domain model, and you encode the knowledge into your types. And instead of using object-oriented tools, you use functional tools. Basically, what you do is that you look, you describe the types of the operations, then you derive or you express laws on these operations, and then you encode your stuff. But it's very akin to a domain-driven design in a way. So with that in mind, how can we model data? And there is a thing. It's not just in the functional languages, and functional languages doesn't mean anything anyway. You can find it in many places, but more in functionally oriented languages, I would say. These are called algebraic data types. Again, a scary word, but it's not that complicated. They're called algebraic because you can think of algebraic data types, which I will call ADTs for now on, as either sum type or a product type. Product is easy. You're using product types every day without realizing it. Product type is like tuples, case classes, POJOs, stuff like that. The idea is that you take different values of different types and you match them together in one new value. They're called product type because if you think about it in terms of set theory, it's akin to a Cartesian product. So you construct them like val_c equals a tuple or case class and then defining that. In this case, the tuple and the user case class, they have the same structure. You can go from one to another, so it's mainly a question of choice and style. And this is a way to construct a value, and this is a way to eliminate a value. Yeah, you can do that in Scala. If you have a tuple, you can do that, and it will deconstruct the tuple and assign the values to the variables. It's okay for everyone? That's simple stuff. And they're called products for a good reason. Is that if you think of types as sets, there is something called the cardinality of the set, which denotes the number of elements in that set. And the cardinality of a product type is the product of the cardinalities of its types. There we have a tuple of booleans. Boolean has two values, true or false. I will not talk about file not found exception for people who read the daily WTF, but anyway. Boolean has two values, and I have a tuple of two booleans. So my tuple of two booleans will have 2 times 2 equals 4 values. And that's a nice way to think about product types. It's just the product of the use types. Okay, so I think you've all been exposed to tuples or POJOs or stuff like that, so that should be quite simple. Some types, on the other hand, are very useful, but not always encoded into languages. A weak form of that is available in many languages, and I'm talking about enums. An enum is a sum. Like a Boolean is an enum comprised of true or false. And in the same way that product types, their cardinality is a product of the cardinalities, then a sum type, it's the sum of the product. If you got an enum, it's 1 plus 1 plus 1. If you got more complex types, then we'll see. Recognize that? What do you think it is? JSON, yeah. And a JSON value is a sum type because you have a closed number of alternatives. It's either string, a double, an object, an array, true, false, or null. And the fact that you got only these alternatives and no other alternative, it means that's a sum type. It's a closed disjunction. In Haskell, it's quite easy to implement because there is like direct support in the language for that. You're saying either have a null or a Boolean or a string or a double and stuff like that. And the number of available JSON values is 1 plus 2 plus the number of strings, and then plus the number of doubles, and then plus the number of other JSON values. So it's basically infinite with constraints on memory, but that's how it behaves as a sum. In Scala, there is not direct syntactic support for disjoint unions, so we'll have to encode it using object-oriented stuff. The alternative part is not that complicated to encode in a function in an object-oriented language. You just have an interface or trait, and then you have every alternative encoded as a class, extending or implementing the trait/interface. The only thing we need is the closed property. Like I know that there will be no other class extending this interface. And in Scala, we have something called sealed, which is exactly that. When you declare a trait as sealed in Scala, then nobody outside from the source file is defined in is able to extend it. So we get the guarantee that there will be no other alternatives than the one we've listed. So either have a null or a Boolean or a string or a number and everything. And the code is a bit overflowing, so it lacks last lines. Is that okay for everyone? It's just like object-oriented inheritance and subtyping with just the addition of being able to restrict it to this file. And to use that, we can use pattern matching. That's nice for that. So if my JSON value is a null, then I return the null string or the string containing null. If it's a Boolean, I will return true or false, and this way I'm deconstructing it with pattern matching, which is different from object-oriented programming, where you would have different methods on every object. With ADTs, we're always deconstructing the top value and then explicitly listing the alternatives. And since Scala is a quite smart language and we've been giving it the information that this trait is sealed, Scala, so Scala as a compiler, is able to tell us when we forget alternatives. So that's only a warning, unfortunately, but at last the compiler is telling something about it. So basically, the message says, you did not handle the JSON string case. Okay. So that's nice. And since the encoding in Scala is not done directly in the language, we gain some extra flexibility compared to Haskell, for instance. Going back to this, these are the legal JSON components, but a top-level JSON value can't be a string or a number. A top-level JSON value has to be either an object or an array. So what we could do would be to create a tab for every type of alternative, and then wrap that into a type saying that's a JSON element, and then just wrapping object and array into another type saying that's also a top level JSON value. In Scala, since we can do it manually, I just have to create a new trait called JSON value and extend it only with JSON array and JSON objects, which is arguably more elegant than just wrapping in 3 different types. Also, in a regular ADT, only the top level stuff has its own type. There are alternatives in Haskell, they don't have their own types. In Scala, since we're using case classes and case objects, each alternative has its own type. So we're able to restrict, if we want only one alternative, then we can restrict in the type system. In Haskell, it will be a bit more complicated to do that. So it's a slight departure from regular ADTs, but used with caution, it can be very useful in Scala. Okay, so going back to OOP. In OOP, the dispatching would be handled by the subtype hierarchy and inheritance. Like, instead of pattern matching on the alternatives, we would just put a common method or like declare the trait, and then the dispatching will be done by the actual implementation. With ADTs, it's different. We do pattern matching, so the dispatching is done by ourselves. In practice, it means that in OOP, it's easy to add cases. Like if you want to add a new case, you just drop in a new class, which extends your interface, and then you implement every method. In FP, on the contrary, it's easy to add function. Like, if you want to add a case, then you have to go through every pattern matching, but if you want to add a function, you just add a new function. Taking the JSON example, an ADT is much better because you're always adding new function on JSON values. You're not always adding new types of JSON values. Like, it's a spec, it doesn't move. So in that case, I find the ADT approach much more suited to JSON rather than a regular O approach. Okay, so another question which arises when you are creating your types is that should you use generic types like tuples or stuff like that, or should you use like always precisely defined types like a case class for everything? I don't have a definite answer on that. My answer would be like use your best judgment. At first, it's easier with tuples because you can just use the machinery available on tuples, and that's all. But at some point, I think it's better to have better encoded safety in your types, and using your own ADTs will make your code more readable, and the presence of mistakes much more unlikely. It's a bit more work up front, but I think it's worth it. So yeah, these two are completely equivalent. I heard the term isomorphic this morning at the keynote. It actually has a very well-defined meaning in mathematics. The word was hijacked by the JavaScript community. But in math, it means basically that two things have the same structure. So a tuple of a string and an int, and a case class containing a string and an int, they have the same structure. You can go back and forth without losing any information. It's just what you put around which matters, but that's the same information. They are equivalent. And it also works for some types. It's a bit more complicated. But with either, which is a standard type in the Scala library. Then you can encode any sum type you want. But you can also declare your own sum type. It's what you prefer. Usually, when I have my need of, when I'm defining a sum type, I will very quickly define my own sum type. Tuples, I will like use, comparing the two, I will use tuples versus case classes much more than regular IDT or regular sum type versus either. Okay, going back to the sum is plus and product is times equivalence. They're interesting to see. You know this? It's called the unit type. And it's called the unit type because, and it has this empty parenthesis stuff, because if a tuple is a product of values, then an empty tuple is a product with no values. And a product with nothing, it's 1. Okay? So a unit type is a type with only one value, one meaningful value. So we call the unit type. And the idea is that if we multiply a value by 1, we get this value back. And a product type between a type and unit is isomorphic to the previous type. And there is another type called void, which is not defined in Scala. It's a type with no value defined. So it's akin to 0. So you can't have a value of type void in your program. So if you think about it in terms of sometimes a plus 0 equals a, and if you get either a or void, then you will always have a because you can't construct any value of void. So it can be useful to think about types in this way because it's much more familiar to us, like plus and times. I've been dealing with that since years, so much more longer than with types. This is called associativity. So whatever the order of the operations, you get the same thing. With tuples, it means that you can flatten out everything and it will be the same. Like, yeah, I can just have a huge, big tuple with everything at the top level, and it's equivalent of nested tuples. And that's the same with case classes. I can either have a tuple of case classes or a big case class with every information in that. So this equivalence allows you to flatten your data. Either you want like a deep graph or a shallow graph. That's up to you. But this equivalence says you that's the same thing. And you've got the same property with sum types. So you can associate everything in every order. And it's the same of the type level stuff. So I can have nested ithers. So if I have an either of nothing I'm interested in, either is like 1 plus 1, or 1 plus cardinality of the rest. So on the left I have this value, and the right I've got another either. So it's 1 plus 1 plus 1, which means 3 different cases. Or I can just have 3 cases. That's the same thing. Okay. This tells you that you can flatten unions and bring all the alternatives at the same level. For instance, in the JSON documentation, it says either you have null or true or false. In my implementation, if you've paid attention to that, I have either null or a Boolean, which deepens, like it puts the true or false inside the Boolean case. But since I can flatten everything, it's equivalent. This one is a bit more complicated. It says like you can distribute multiplication over addition. And with tuples, it says I can have a tuple of value of type string, and then an either, or I can move the either on the outside. Which means you can actually factor out, like literally refactoring code. You can do that with ADTs. It's like we use refactoring to move stuff of code, bits of code everywhere. In this case, it's like literally factoring, like in math. And that's the same thing with enums. If we have like 5 alternatives which the same structure, we can factor it out as a tuple of an enum and the type. So in this case, these two lines, these two stuff are equivalent. Either I have 2 case classes with a string, or I have both a string and a boolean. So this allows you to like extract a tag as an enum or put it into a sum type. And this one is a bit more complicated, but basically it says you can do case analysis. If we have a function from A or B to C, it's equivalent as a function from A to C and a function from B to C. So that's case analysis. Like when you're doing a pattern matching or using fold or stuff like that, you're using this equivalence. Okay. Since I'm talking about booleans, avoid them. If you Google Boolean blindness, you will find a very interesting article saying why Booleans are a bad thing. Basically, Booleans carry no information. A Boolean can come from anywhere. An enum with properly defined values, you have to construct it to be of this type. A Boolean, like it can literally come from anywhere. So avoiding Booleans will make your programs more precise and more type safe, basically. Read the full article, but that's the gist of the idea. Okay. Going back to functional programming is programming with values. Of course, at first it's easy to do, like pushing ints and stuff, but we're able to push much more information into values. We're able to push context. And with context, I mean, has an error arisen? This operation is non-deterministic. I'm talking through the network and stuff like that. First example with error handling. In Java, you've got either checked exceptions or unchecked exceptions. So you still have any checking in the type system. In Scala, everything is unchecked. So you don't have any information on that. So the first step, or first solution, will be to use the option type. Like if you're following Java 8 stuff, it's called optional in Java 8. Basically, it's a sum type. Either you have a value of type A, or you don't have anything. So it allows you to encode the possibility of a null, but in the type system. And in Haskell, it's called maybe. So I just wanted to put these GIFs, sorry. The problem with option is that there is only one case where your value is not defined and it says something went wrong. What went wrong? I don't know, something. So you can only use it when only one thing can go wrong. For instance, if you're trying to parse a string as an int, you can say that the only thing that can go wrong is that the string I'm trying to parse is not a series of digits. That can be a good thing. If you want more information, there is either. Either is defined in the standard library. So with either, you've got either a left or a right. By convention, right contains the expected value, and left contains the error. So the expected value is the expected value, nothing to talk about. To describe the error, you can use an ADT. Maybe just an enum, maybe a full-blown ADT. That's also why I'm not talking about try. Maybe if you're writing Scala, you know the try construct, which is basically the same thing. The problem with try is that the error type is always throwable. So you're not able to really act on the error because you lose information. With an either, you can put the type you want. So you can put an ADT. So this kind of code, either string something, that's a code smell. Because when you construct the error, yeah, when you construct the error, you have information about the error. If you pass it down the line as a string, then you're erasing all the information, the structural information you had about your error. So it's much better to encode it as an ADT. Like for instance, I know that the code that produces the error is either missing username or invalid email. I know that if I handle these two errors, then it's OK. So that's very, very interesting to keep structural information about which errors can happen. If you use exception and check the exception and stuff like that, then anything can happen and you lose that information. So in my code, I can say, yeah, if I got a right, I do a thing. And if I got a left, I'm missing username, I know what to do, and invalid email, I know what to do. And then the compiler is able to tell me if I've forgotten to treat an error case, which is very hard to do with a throwable, because you lose information. There is a thing to note about the either provided by Scala, is that it's not biased. By biased, I mean, by convention, right is supposed to handle the good case and left the error case. So when I want to chain ithers in a for, I want it to chain on the right and stop at the first left. So to do that with Scala's either, I got to put right at the end of the line. OK, and the way it works is that as long as you got right, then it continues, and at the first left, it will stop. So it stopped at operation 2, and operation 3 is not executed. Which is a bit like exceptions work. As soon as an exception is thrown, then the following code is not executed, and you stop there. Another problem with either is linked to the way ADTs are encoded in Scala, is that in a sum type, every alternative has its sum type. And it messes with type inference. This way, the compiler infers the type to be a left, and then I give it a right, and it's not happy. But what I wanted to do was to give it an either. So it was too strict in the inference, and it causes problem. And that's like a usual case of frustration when you're working with either in Scala. And yeah, there are small quirks like sometimes instead of having an either, you get a product with serializable with either, and that's just craft. I don't need that shit, so I just want my either. This is why in the wondrous library called Scala Z, there is something called // Sorry. You can call it Scala Z disjunction. It behaves globally as an either, but in better ways. So first of all, it's biased, so it will automatically assume you're interested in the right. And the constructor gives you the value typed as disjunction, not left or right. So you don't have any inference trouble when using this. So it works the same way. It fails at the first left. OK? Once again, I want to remind you that this is an expression. So I'm able to handle errors as expressions, which is very, very powerful because I'm able to write libraries handling errors and stuff like that. Everything is an expression is a very, very powerful pattern. But there is something to understand, is that either and disjunction, they fail fast. And that's how exceptions work, but that's not what you want every time. The seminal example for that is I was like lazy when doing the screenshots. Imagine like a 20 field, 20 input form, like the kind of stuff that takes you 10 minutes to fill in. And you fill in your form and you submit it. Oh, there is an error in the first field. You resubmit it and there is an error in the second field. And like, just tell me all the errors. Like, I don't want to refresh a page for 15 minutes just because you're like a bad programmer. And either and disjunction, they forced you into this model. Sometimes you want to be able to accumulate errors, like try out different things in parallel and then give back all the errors. You want to accumulate them. And for that, there is something called Scala z.validation. That's a nice thing because it actually has a name with letters, not symbols, which is nice. And the way it works, it says I'm returning something called validation null with a string as an error type, which is a bad thing. Don't ever do that, sorry. And the string as the expected value. So if I'm happy with my value, I return a value that's success now or an error that fail now. The null means non-empty list. You've ever had this kind of error message like error, no error? Yeah, so the validation null has a non-empty list of errors. So you can't have an error without an error. So you've got to have at least one error, which is very nice. And to use it, yeah. So I have a validate email returning me a validation null of email and a validate username returning me a validation null of username. And I combine them with like little operator called the home alone operator or the cinnamon bun operator or the munch cry operator. Like it has many names. Anyway, it allows me to combine together validating functions, and if everything goes well, then I got my values. Okay? And if something goes wrong, then I get a non-empty list of errors. And if two things go wrong, I got my two errors, which you can't have with exceptions or with either with disjunction. And that's very, very, very nice. Especially with web forms, you want to like handle every form in parallel. You don't want to block on the first error. And to encode your errors, you've got either or validation. And it's not a bad thing to have different levels of errors because you want to keep that information. Is that a user input error? Then you can have a series of enum for that. Is that a database access error? Okay. But if you got user input errors, you may want to accumulate them. If it's a database access error, then you want to shut down the computation. So you may want to mix either and validation. So do not always try to like mash out every single possibility of error in the same data type. That doesn't make sense, or not always. Okay, that's all for the errors handling. The next subject is how to do extensibility in and polymorphism in functional code. Because you can't just like inherit code and stuff like that. What we want is ad hoc polymorphism, but a little less ad hoc. And for that, there's something invented in the Haskell world called type class, which allows you to have extensibility and abstraction. My example for this would be the monoid. The monoid is also called the big data type class for a simple reason, is that if you have a huge pile of computations to do, you want to parallelize them and compute small parts of the computation on different nodes and then assemble back the results. Basically, when you do MapReduce, that's sort of what you do. And the monoid is an abstraction, a mathematical abstraction that expresses exactly that. A monoid allows you to combine two values, and it allows you to do that with associativity, which means if you have a huge chain of operations, then you can do the intermediate operations in any order you want. You have the guarantee that the end result will always be the same. So associativity allows you to distribute work. That's very important. And it also has a neutral element, like plus and 0, times and 1, stuff like that. Okay, a first try, a first object-oriented try. Let's say we create a trait monoid, and it defines a method that takes another monoid and returns a monoid. So we create a class, it extends monoid, and then, yeah. There are many problems with that. The first one is that it takes another monoid, but lots of things behave as monoids, so we don't want to take every monoid. So you lose information, because it's like the equals in Java. Since it's defined at the top level, you're forced to take a java.lang.object, and you can't force the compiler to accept only comparing for equality two values of the same type. So that's the problem. You lose information. Another thing is that you can't have behavior to final classes. Like if you want to add behavior to ints or to strings or stuff like that, then either it's not final and you create a wrapper and you have to use your wrapper everywhere, which is not nice, or it's final and you just wrap it with composition instead of inheritance, and you have to like make everything go through a proxy. Another problem is that how can I encode the 0 with the monoid? Since the monoid is declared as a trait extended by the monoidal values, I can create a value out of thin air. The solution for all these problems is to have external declaration. You have your data type, you have your behavior, and you declare externally how your data type behaves. Okay. To declare the behavior, we create a trait. The trait is called monoid, and the square brackets, it's like pointy brackets in Java, it's generics. So my trait is parameterized by the actual type of what will behave as a monoid. And it says, I have a function which returns a value of type A, which is 0, and then I have a function taking two values of type A and returning a third value of type A. Okay? With that, I don't have any problem with final types because I'm not extending another type. I'm not losing information because everything is kept in the type parameter. So everything is still a A. I don't lose information because of subtyping. And to implement it, I just create a new value of type monoid of string, and then I put all my behavior in that. Okay? Like I create like a dictionary of all what's needed for a type to implement this behavior. For a monoid, I need two things: a 0 and a way to combine two values. I have my dictionary. I declare what is 0 for a string and how to combine two strings. And to use it, I pass this dictionary to the function that needs it. So I have a list of values of type A. I want to combine them into one value. I can do that, which is because it's a monoid. I start with 0 and I combine element by element. And then I just say I want A to be a monoid. and then I'm able to use it. So in this way, I have a sequence of strings. I pass the string monoid, and it concatenates everything. I have a sequence of integers, and I say I want the monoid with addition and 0. It gives me an addition. And if I want to have the monoid for multiplication, then it multiplies everything. Of course, it's not very practical to manually pass the behavior. So we can have automatic wiring, and we implement it with a thing which is always a good solution in Scala. If you're not happy with your Scala code, just throw some implicits at it. That's always a good solution. So I make my behavior declaration implicit, and then in the code that needs it, I just say that will be provided. Implicits allows me to pass values implicitly to function. It's resolved at compile time. So when I say I want an implicit value of type monoid A, at compile time, the compiler will search for an implicit value of type monoid A, and if it doesn't find it, then it's a compilation error. So then I'm able to use it this way, or either this way or this way. It's basically the same. You can see the two used. So in the first case, a string has only one way to behave as a monoid. That's OK. For ints, since we saw there are two ways for an integer, or maybe more, to behave as a monoid, then we can't just decide the implementation just by looking at types. And that's a problem in Scala called the type class convergence. The good practice is to have only one behavior for one implementation for a type and a behavior. If a type has two implementations for the same behavior, what we usually do is we create type wrappers which are eliminated at compilation, but in your code it's different types, which is a good thing because then you know how the types behaves for this behavior. Okay. A very, very good use of type classes is serialization, because you don't always have control on the values you're trying to serialize. You're mostly serializing ints, strings, and stuff like that, and you don't have control about it. So I don't know if you know the shapeless library. It's a very good library in Scala for doing type-level magic. And basically, its creator tried to use Spark once. And Spark, for its serialization, requires to use Java serialization. So it requires to add extensible. So basically, my subin had to modify its library because Spark was not able to serialize it. And that's a big problem. There is a huge commit where he had extensible everywhere, and it must have been very painful. With type class-based serialization, you declare this behavior outside from the type itself, so you can add it as you wish. Going back to JSON, let's say we want to transform an arbitrary value into JSON. Then we create a behavior called toJSON, and it has a function which allows us to transform a value into a JSON element. Okay? Then, let's say we have a map of string and a value of type A, which I know how to serialize to JSON. Then, the nice thing is that code implementing the behavior for very default types in Scala, like map, is able to pull my implementation of serializable for my own types. So with type classes, you're able to wire in your behavior into default behavior very transparently, which is very, very powerful. And if you use Play Framework, type class-based serialization is central to its design. Of course, there's JSON. There are also type classes to say, I want to serialize this object to the DB. So You declare or you transform back and forth between your objects and your rows. If you have stuff in your query string, like I want to put a date time in my query string, I just have to write the implementation saying how to go back and forth from a string to a date time. And you can also do that with forms. So it's very powerful. Every time you get to go through serialization, type class is a very, very good tool to help you do that. And if you want to use Scala Z, which is an extension to the standard library in Scala, every abstraction, like monads, functors, stuff like that, it's encoded as type classes. So once you're able to recognize the pattern of a type class in Scala, then you can go read the easy parts of the Scala Z code, and you will be able to understand how it works. So there is another part of type classes, which are laws. It says, for instance, with monoid, associativity, and neutral element, you can't encode that in types. So the idea is to encode these laws into property-based tests. Instead of having regular unit test, you say A goes in, I want B to come out. You say, given values, I want these properties to hold. A regular unit test, it works as there exists. You show the presence of bugs into test cases you've chosen yourself. With property-based testing, it's like for all. It's not mathematically exhaustive like types, but you're delegating the responsibility of providing the test cases to your test framework. Let's see a simple example with Scala check. I'm concatenating 3 strings, and I want to make sure it concatenates them okay. So I just ask my test framework for 3 strings, I concatenate them, and then I check a property. But my test case doesn't depend on the actual string. It just checks for a property that should hold for any strings, or any triplet of strings. So it's very powerful, and if you're able to express this your information, your business logic into property-based tests, then you reduce your amount of tests, and you've got better coverage for edge cases. So it's a very interesting tool, and it's very nice. So it's called Scala check. Very cool. Okay, and the last part is how to separate effects from logic. The idea is to separate making decisions from acting on these decisions, like computing a value from persisting it into the database, for instance. And what you should do is that you should encode all the actions you want to actually make on the outside world as an ADT. For instance, instead of just adding a user to a database, then you produce a value of type addUser, and then you pass it to a part of the program which is responsible for acting on these operations. You can do that for amount transfers. So you declare actions, your code with business logic, it creates values representing actions, and then you interpret them, as we say in the functional programming community, at the end of the world. Like, when there is nothing else to do, then you do the side effect and stuff. Of course, why bother with such complicated code? First reason is testability, because if you want to test your business logic code, then you just have to inspect the stream of actions demanded by this code. You don't have to mock database and go through like huge pile of hacks that we're kind of forced to do in object-oriented programming. You also gain great flexibility, because you're not forced to actually execute any action. You can merge values, you can reorder them, stuff like that. So you're able to act on the decisions before they are persisted. And if you're persisting all these demands of action, then you can go back in time. That's one very good thing with event sourcing. You persist all the events, and then you're able to like go back in time and reinterpret these events with different codes, or saying what would have happened if that event wasn't there, stuff like that. So by persisting every decision you make, then you're able to go back in time, actually, which is very good. Okay, to wrap up. First thing, in functional code, we tend to modelize our data with algebraic data types rather than standard type subtype hierarchies. So it gives us closure, and we can inspect them with pattern matching. Try to materialize errors. It's very good because then you're able to use libraries handling them afterwards. Have a look at type classes, especially for serialization. And if you want to try Scala Z, it's very important to understand what a type class is. Property-based testing is very, very nice. And then the last step is to segregate effects. It takes some time to do that. You won't just go in a side effect-free system for your first project. You need to be confident with functional programming to do that. But once you do that, then your code is much more simple and very easy to extend and way better, way simpler. Okay, if I didn't scare you and you want to learn more about it, there is a book called FP in Scala, edited by Mannings. It's written by Runar Bjarnason and Paul Cusano. It's a little red book, Functional Programming in Scala. I recommend it a lot. It's a very, very nice book, very easy to read, and it gives you very interesting insights about how to design a program functionally. So there are not enough books like this, so if you want to be serious about Scala, read this book. It's very, very good. And that's all. Thank you for your attention. If you like the GIFs, they're available online. And if you want to try Clever Cloud, there is a coupon. Just input DevOps rocks, and you will be able to extend your free trial on Clever Cloud. Thank you. I have 5 minutes for questions. And I have a mic for questions. A not working mic for questions. So if you have questions, I will just repeat them through the mic. No? No questions? Okay. So it was perfectly clear.